Okay, so we're going to do 437, and we have this diagram here, and what we're looking for is the moments about O, the moment about O that F causes here. All right, so O is here, we have F here, and it's kind of pointed in a weird direction here. We know that the magnitude of F is 800 newtons, and we know the component angles, coordinate directions of this F as alpha 60 degrees, beta 120 degrees, and gamma 45. So let's just write out F here. So F is equal to a magnitude of 800 newtons, and then we need to break it down into its components. So in alpha, right, that's the angle between the vector F and the x-axis. We have cosine 60 degrees. And for beta, and this is the I direction, and then for beta we have cosine of 120 degrees, and that's in the J direction. And lastly we have the Z direction, so we have cosine 45 for gamma in the K. Okay, so we can expand this out. We take 800 times each one of these components here, these cosines. So we have the vector F is equal to, let's find it. So we have 400I negative 400J and 565.69K. Okay. All right, so why did we need to do that? Well, this is the coordinate, Cartesian coordinate interpretation of vector F. All right, so usually when we find moments in the 2D space, we're usually keeping track of clockwise and counterclockwise components to it. And when we move to 3D, we really have to use the cross product here, the cross product version of the moment. So what we're trying to find here is the moment about O, and this is a vector even. So I'll just write vector here. Okay. So to do this, we use the moment around O is equal to the cross product of R cross F. All right. And we already know F here. We just solved for that. But what is R? Well, R is the vector that starts from the point you're taking the moment about, which is O, to the location where the force is applied, and the force is applied all the way down here. So the vector R, I can draw a straight line there. The vector R is from O to down here. Let's just call that point A. All right, so this here is vector ROA. Okay, so to solve this problem, we already have F, we need to figure out R. So R from O to A, and we need the components of this. So we first look at the X direction. So from going from O to A, in the X direction, so the X direction is this way, we're actually moving 0.4 meters. So it's 0.4 I. And in the Y direction, we're moving from O to A, and the Y is this direction, so that is 0.5 J. And lastly, in the K direction, or the Z direction, from O to A, we move downwards 0.3 meters. That's negative 0.3 K. All right, now all that's left in this problem is to perform the cross product. down just a hair. Okay. Things around so we can see. Okay, so here we go. All right, to perform the cross product, what we can do is write the R vector, ROA, and so the R vector is 0.4 and 0.5 and negative 0.3. Okay, and then the F vector is 400, negative 400, 565.69. Okay, and I'm going to show just a kind of a different procedure for performing this cross product by hand. You can use the one we went through in class if you wish. So I'm just going to repeat this vector again, the R vector, 0.5, negative 0.3, and then repeat the F vector again, which is 400, negative 400, and then 565.69, 69. Okay, so to perform this cross product, all right, we kind of leave off this column and this column over here, and we perform the multiplication of 0.5 times 565.69 minus the multiplication of negative 400 times 0.3. So 0.5 times 569.69 minus negative 400 times negative 0.3. And that comes out to be 163. Okay. Then we just move down the line. We perform negative 0.3 times 400 minus 565.69 times 0.4. Right, so this times this minus this times this. And for that we get negative 346. And then for our last one, we perform 0.4 times negative 400 minus 400 times 0.5. Okay, and if we do that, we get negative 360. Okay, and that turns out to be our answer. So this is the moment is equal to 163I minus 346J minus 360K. All right, and that's our answer. And that is 437.